everybody. Today we are going to start a new module in the course of supramolecular chemistry, and in this module we are first going to start with self-assembly processes in nature. And here we are going to first start at understanding the principles of self-assembly, principles of SA. I can use just the short form SA, and we are also going to look at metal complexes as model systems to understand SA processes, that means self-assembly processes, and then we will look at some specific cases of self-assembly in biological systems. So this is going to be quite an extensive discussion on self-assembly processes, and we need to actually first start understanding what is self-assembly. Till now we have been focusing on events related to molecular recognition, supramolecular chemistry between different kind of species via intermolecular interactions. Self-assembly is also an extension of the understanding or the knowledge which has been derived from supramolecular interactions. But in this particular exercise of self-assembly, the manner or the mechanism in which the process proceeds is done in a very specific way, and it actually follows a series of sequences or a series of instructions which are actually contained within the system, or which are actually programmed within the system, or you can say they are coded in the system, such that the species or the molecules or the different atoms and ions first recognize each other in specific ways to form specific species, which then further assemble to give you the larger architecture or the larger species. So it is not that the self-assembly process is not more of a random process or a randomized process where statistically you have a set of species in solution, and then they will the molecules of the species will come close to each other or collide with each other and then form a certain set of structures. It is more programmed, it is more of a precise recognition process, and that is why we need to understand the principles of self-assembly in a more rigorous way. So to start with, let us look at a definition of self-assembly. So in this particular lecture we will be taking down a few very important points or notes related to self-assembly, so that we are more familiar and comfortable with the language which is used to understand self-assembly. So this is a process, the process that involves the spontaneous association of two or more molecules or ions to create a larger aggregate species through the formation of, this is a very important point, through the formation of a reversible supramolecular interactions. And the process of these supramolecular interactions or events of reversible recognition depends upon, this is in accordance with the information encoded in the system. And so this is the definition of self assembly. So to start with, let us first consider events related to processes of self assembly in metal ligand complexes. And first of all, we will look at synthetic probes or examples to understand molecular self assembly processes. And why we are choosing metal ligand complexes? Number one, because they have lability associated with them, that is, the metal ligand bonds are of a labile nature, and number two, they are also characterized by a high degree of directionality. Okay, and the directionality is because given a metal ion and a given ligand environment, we are able to predict with confidence and certainty the nature of the metal ligand association to form a much larger aggregate or larger species. For example, let us consider the following ligand. So we have nitrogen as the donor atoms, and we consider 4 equivalents of these, and we consider 4 equivalents of a palladium complex with ethylene diamine. This is the corresponding palladium species, and now we know that palladium tends to form a square planar complexes having coordination number 4, and so in this regard we see that this palladium center can now form 2 additional p-n bonds from these 2 particular directions. So this can come from now this particular pyridyl bipyridyl system, it can come from here. Then we can have another palladium nitrogen. This can form So now you can see we have formed this larger species. We have formed this large size species, and the overall charge on this complex is 8 plus. And this is referred to as a molecular box. This is referred to as a molecular box, and you can see that there is a void here in which you can have different kind of solvent molecules which can be included. So we see that this kind of a very specific association takes place between the palladium center and the bipyridyl ligand to give you this molecular box. This is more specifically referred to as a molecular square, and this square can now aggregate further in solution to form a molecular box kind of an arrangement. So this molecular square is formed, and this process of self assembly now leads to the formation of a thermodynamically stable product. It leads to the formation of a thermodynamically stable product given a set of reaction conditions. So there could have been the possibility of formation of a species. Say if I take it, it could have also formed this kind of a species where you have two of the nitrogen centers coming from the two bipyridine ligands, and it could have formed half of the species. So, it could have formed this particular species, which is itself satisfying the valency at the palladium center, that is the dsp2 hybridization and the square planar geometry. But then we also have another such species this side, which also is the square planar palladium, and now because of these two specific nitrogens which are at this particular site, they can now satisfy the coordination requirement of another palladium center, and therefore this particular box is now being formed. So, you see here that when you had this particular species here, this particular site was for palladium was empty. So, the palladium here had 3 valency. So, the fourth one comes from this nitrogen, here also the fourth one comes from this nitrogen. It forms a molecular box, a very specific arrangement, and which has got the greater thermodynamic stability. So, keeping in mind these features associated with metal ligand complexes, let us look at the other characteristics of self-assembling systems. So, the final product formation takes place in a series of steps. Okay. First, first we have the smaller aggregates, then they self-assemble to give the larger aggregates, which lead to the formation of the stable product. So, first is the formation of the metal ligand complex, and then further supramolecular processes can happen before the species can assemble further with each other. And the next thing which is important is that there exists multiple equilibria between the differently formed species, and this can be influenced by concentration and temperature of the experiment. So, for example, we know that when we have a metal, it combines with the ligand, it forms Ml first, then Ml combines with further ligand to give Ml2. In this way, we finally get the Ml6, and eventually we know that the beta is actually the product of the equilibrium constant for each of this particular step. So, each step here having the constant K1, K2 like that influences the magnitude of the equilibria and influences the product formation. So, the overall equilibrium constant is a product of the constants for the individual reactions where the individual equilibria exist, and this can be influenced by concentration and temperature of the experiment. So, overall the driving force is the formation of the thermodynamically more stable product. The next thing is that when you have self-assembly processes, more than one type of interaction will participate. More than one type of interaction will participate. For example, you can have the combination of metal ligand interactions and also hydrogen bonding between the atoms in the complex. Again, the process is to form the thermodynamically most stable product. The thermodynamically more stable product. And finally, this is a very important feature of a self assembly. We are utilizing interactions with different strengths. For example, the metal ligand bond is the strongest, and then we have the strong hydrogen bonds, we have the medium strength hydrogen bond, and the weakest of interactions. So the spectrum of interaction strengths operate, and then by utilizing these interactions with different strengths, we can design large supramolecular arrays such that this specific information or memory is encoded in the system of interest. Okay. This results in the formation of an ordered assembly in a particular manner to form the thermodynamically stable product. So all the points are actually directed towards the understanding of the formation of the thermodynamically most stable product via the process of self-assembly, and highlighting the role of concentration, temperature, the different types of interaction based on the interaction strengths, and this will actually guide the process of self-assembly. And this is also referred to as the process of hierarchical self-assembly. Hierarchical means it is taking place in a specific manner, in a specific fashion, and this particular information about the specificity of the interaction strength is actually encoded in the system of interest, which overall now results in the formation of a highly ordered supramolecular array, resulting in the formation of a thermodynamically very stable product. And so self-assembly means there are a set of specific instructions given to the system that is contained in the memory of the system, and then the system operates utilizing these well-defined set of instructions. It is just like a computer which operates given a set of instructions. So here also the process of self-assembly is very specific, and if there is any mistake which happens during the process of recognition or self-assembly, because the reversibility of the process, the system can then dissociate and then correct again the process of recognition, so that the self-assembly takes place in a proper fashion. So this type of memory in the system, so as to erase off any wrong association or wrong atom contact and then create again the relevant atomic contact, is what makes self-assembly processes very unique, and they have got implications in nature. So self-assembly, and that is why the process of reversibility is very important. That means if by mistake we have formed a particular contact or an interaction by either thermal processes or statistically random processes, the system gets an opportunity to repair or correct itself, so that it can now again form the relevant contact of interest, and the process of self-assembly continues to give you the finally highly ordered structure, which is the thermodynamically most stable product. And in this regard, what is important is, as I told you, hierarchical self-assembly. Hierarchical self-assembly, where there are several levels of complexity that operate over several self-assembly processes. One level cannot exist without the existence of the preceding one. This is very, very important. The process and the directions, this is in quotes, that is the process is very important, and the directions which are to be given to the system to be followed during the process of self-assembly has already been programmed into the system. And takes the system in a linear fashion, serially, stepwise, from a high energy state to a lower energy state. Okay. So, I hope you have been able to appreciate the principles which govern self-assembly processes. Now, there are classifications of self-assembled systems. Classifications of self-assembled systems. So, first is the single interaction self-assembly. In the case of single interaction self-assembly, we also call this the single code self-assembly. It refers to the existence of only one specific interaction. For example, you can have a system where the species interact via only OHO hydrogen bond or OHN hydrogen bond or NHO hydrogen bond, and so on and so forth. Or you can have palladium nitrogen interaction of a given type, of a given specific type. So, all these are examples of single interaction self-assembly. And then we can have multiple interaction self-assembly. The process in which more than one type of interaction is present, more than one type sorry, I need to correct here a bit, more than the process in which more than one interaction of a given type is present, it is referred to as multiple interaction self-assembly. So, a given type of interaction is there, say palladium nitrogen or OHO, and the number of such interactions that are present is more than one, and that is why it is called multiple interaction self-assembly. So, a given type of interaction, but the number of such interactions are many, are multiple, and therefore it is called multiple interaction self-assembly. And this can be further divided into unimediated or multimediated self-assembly processes. And this is if you have got only one type of interaction, it is unimediated, but if you have got now multiple types of interactions, then it is multimediated. For example, you can have both palladium nitrogen interaction plus OHO hydrogen bond, then it becomes a multimediated self-assembly process. So, if there are now different categories of interactions, so this is one category of interaction, this is another category of interactions, and also their numbers are more than one, then this is referred to as a multimediated multiple interaction process. So, multimediated multiple interaction self-assembly. And if you have these interactions which are of different types which are present, but there are multiple interactions of a given type, we can call this as unimediated multiple interaction. So, in this case you will see that if you have a given type of interaction, say either palladium nitrogen or OHO, but they are present multiple times, say they are present 2 times or they are present 3 times, then they are of a given type, but they are present multiple in number, they are called unimediated multiple interactions. Here there are of different types and multiple numbers of each type is present, they are called multimediated multiple interaction self-assembly. And there is a tendency to actually use multimediated and multiple interaction self-assembly interchangeably, but now we should keep in mind that they are actually different, different terms, and they should not be used interchangeably and should not be confused. That is, multiple interaction assembly is different and multimediated assembly is different. So, let us look at some representations of these. For example, we can have a metal here and a metal here, and it is interacting in a particular coordination environment. So, this is you have got metal ligand interactions, and therefore, this is single interaction assembly. This is a single interaction assembly. We have got the same type of metal ligand interaction at all the regions. But now we change So, now we see we put a metal here, we put a metal here, we have put a metal here. So, we are going to have now, so this is a different environment and this is a different environment. So, we have got two different metal ligand interactions, but the type is the same, So, although we have got two different metal ligand environments, they are still referred to as unimediated assembly, because although there are distinct interactions, there are different types of interactions, they all belong to the same type. So, because the type is the same, that is, there is only one type of metal ligand interaction, but they exist in different coordination environments, we call it unimediated multiple interaction assembly. Okay, and now in the third case, what we can have a case where we have say for example, here we can have OHO hydrogen bond, here we have metal, and here we again have metal. So, here we can see that now you have got two different types of interaction. So, we call this multimediated multiple interaction assembly. So, these are the different types of interactions that we can have now, and given these kinds of self assembly processes, now we can look at the formation of different kind of discrete large size discrete species, and in this regard we have got a classification that is based on the formation of metal ligand complexes, wherein we can now look at the formation of ladders, polygons and helices. And so, as we told that in this regard we need to have metal and the ligand in a certain coordination environment so that they can form a discrete species, and different kind of building blocks have been proposed, and in this regard let us look at a couple of such design elements to make larger size of discrete species. For example, we can have a metal. A metal we know is divergent in nature, and we can now have a ligand which has got the convergent sites, now convergent sites, and therefore now we can have a process of self assembly where we can have the metal which can come here and now form a discrete species. And in this case we have two such equivalents of the metal and two equivalents of the ligand. So, we see that the numbers actually now add up statistically and they form a much larger size species, and to start with entropically this is not very favored because it reduces the number of units, but then what is important is the number of enthalpically driven metal ligand interactions which drive this process. Similarly, we can have a different kind of a design where we have a metal and we have the ligand which is protected, and now this is a convergent metal because there are only two distinct binding sites and they must approach the metal in a converging manner, and now the ligand actually is open. So, the ligand has got divergent sites and we have got a protected convergent metal. So, this can now lead to the formation of a very specific discrete species where we can now have so this is the ligand here and this is the ligand here. This is something we looked at in the case of the molecular box where we had the palladium which had the two nitrogens coordinated, and then two more nitrogens can come and coordinate and stabilize the species. Obviously, it led to a larger box, but we can have these discrete species which are formed. And the overall chart depends upon the oxidation state of the metal ion and also that of the ligands. And we can have a third one where we have a divergent metal and we have a divergent ligand which can actually give rise to a polymer. So, these are the different kind of design principles which can be followed in the construction of large discrete species involving supramolecular assembly. So, in the next lecture we will now take up examples where we will look at more realistic examples of such chemical entities which form these supramolecular self assembled building units. Thank you.